What we're going to talk about today is this issue to contributions to pollution, especially by particles in the atmosphere known as aerosols. And that's why this particular group is assembled. So the first speaker today is my colleague in the Department of Chemistry, Dr. Kimberly Prather, who's been with us several years now, who had been a professor at the University of California at Riverside, where we were fortunate to recruit her to come here to the southern extreme of California. Her background in the beginning in graduate school is very interesting in this field that a lot of people that work in it weren't originally trained in it. And her background was working with another famous person up in the Republic of Berkeley and training in using the most sophisticated instruments in physical chemistry, which she now has applied in a special way to measuring these particles. And as you'll hear, what she's internationally famous for is the ability to measure one of these particles at a time, which you can't see, in real time, continuously. No one else could do this. She's the inventor of this technique, and it's changed the way people think about this and the various issues you talk about. So, Dr. Prather, it's all yours, and I'll turn it over to her.
All right, well, first of all, I'd like to welcome all of you to UC San Diego. I was asking Professor Molina how to say climate in Espanol. He said climat. So anyway, today I'll be talking about climat and filling you in on, as Professor Thiemens indicated, on some of the research we're doing in our group. This is actually a picture taken. We live in beautiful San Diego and don't have many days like this, but this was actually taken on campus during the wildfires in 2007. So I'm going to focus a little bit on this aspect of air pollution today. So basically, just a little bit of background on the research that I do, or my group does at UC San Diego. Basically, what we're focusing on, and the topic of this workshop, is looking at aerosols. And these are just the examples I'll show on the next slide, but they're bits of dust and smoke and the things you can visually see. They're the things that are blocking our visibility. So when you have a very high pollution region of the world, it's usually the aerosols. It's not the gas phase species that we're used to thinking about, like ozone. Those are completely invisible to the naked eye. So basically what we've been doing is performing studies. We do lab studies, but we also do field studies. We started out in the lab, and now we've shrunk everything down and take it out into the field, and I'll discuss these just a little bit. Around the world, trying to understand what is causing sort of this overall pollution levels that are rising. I mean, we know it's us, but what are the main sources of air pollution around the world? And these are just some of the places that we've done measurements in the world. The yellow dots or square stars are places we've gone. The green are places that now other institutions who now are using our instrumentation are making measurements. So basically, we've done them on every continent except for this one. And I know, as I say, a lot of you are interested in this area, and I will tell you that we're now shooting to do a study in 2010 in the Amazon, in the rainforests. So what are the different sources of aerosol particles? Dust is something that we can visualize from satellite images. Pollen is a natural type of aerosol. Biomass burning or wood smoke. This one's a tricky one because it could be man-made or it could be, natural. So wildfires kind of fall in between, depending on whether we're the cause of them. Vehicle emissions, a big one, at least in the United States, we think about a lot, are trucks, and we've implemented a lot of restrictions on these because they were our #1 source for a long time. They're not anymore. I think ships have actually surpassed trucks based on some measurements that we've been doing. Industrial emissions, depending on where you are, these can dominate at certain times of the day. And sea spray is just a nice natural one. We think it's nice. We're actually thinking about studying the health effects of the spray that comes out of the ocean. So there's really the sad news of this talk is that there's nowhere that you can really go in the world anymore and not see evidence of air pollution and transport of aerosols. Riverside, California, which is where I came from, has it virtually every day. So it's very impacted, has very similar mechanisms that are controlling the pollution as Mexico City. We've also done a study, which I think Professor Molina will mention a little bit, Milagro in 2006, and I'll talk a little bit about that. We went to the Maldives Islands off of the tip of India. We went there because we were looking for a pristine place to do studies of background air. But unfortunately, as you can see, even there, it's hazy. And even when you go up into the Arctic, you can see that long-range transport is causing pollution to get all the way up into an area that doesn't produce their own pollution. And so this is an area of major concern. And the question is, what is causing this? Is there sort of a lot of different things, or is there some uniform, factor that's contributing to this haze that we can hopefully fix? So just to give us evidence, if we stand way back and look at satellite images, we can see that basically dust is one of the things we hear a lot about. We get export of dust from China and Asian pollution all the way to the United States. So we import our pollution, as Professor Thiemens mentioned. But we export our pollution to Europe. And so, the key lesson is that the atmosphere has no walls. So it's not like, it's not like water or something where it's just contained locally. Air pollution is transported all around the world in the matter of days. So California wildfires, and also this is actually dust off the coast of Africa. This is one of the reasons we're going to the Amazon. This just happened, and this is dust that gets exported to South America, and they believe it plays a role in fertilizing the forest. And so that's one of the things that we will be looking for when we go there. So these are all events that have just happened within the last couple of months. And you can see, as I say, this is standing way back. You can see that these are very dominant types between biomass burning as well as dust. And these are surface areas upon which chemical reactions can happen, and it transforms the chemistry of the entire atmosphere. So without these surfaces, our atmosphere would be completely different. And this was shown actually to be very important in the stratosphere by Professor Molina. It's one of the reasons he got the Nobel Prize. They showed that surfaces were important in the stratosphere. Now we're starting to try and understand the importance of surfaces in the troposphere. And they're equally important, but we are far behind in understanding the reactions. They're a lot more complicated close to the ground. So what do we know about climate? We know a lot about the greenhouse gases. We hear about those all the time. And climate and greenhouse gases sort of go synonymously, hand in hand. When we think about climate change, we usually are talking about CO2 for sure. But we are trying to understand the aerosols because this is the part that's the least understood by far. It's not even a close call. And that's because aerosols are really complex chemically, and their size and their shape. And all of these factors go into affecting whether they're warming or cooling the atmosphere. They can do both. And whether they do one or the other, that's the part we're a little uncertain on. And so when we sort of try to predict how the temperature is changing over this course of the century and where we're going to be, I'm sure you've all seen the really large uncertainties. We don't really know how much warmer things are going to be. Most of the uncertainty comes from the aerosol component. Okay, so they can warm or cool. They also form clouds, which is an even less understood process. This is the effect of large volcanic eruptions, which make sulfate aerosols that exist for quite a while. So this is the percent change in temperature when these different eruptions have occurred, and you can see that the temperature has decreased for a few years. And so basically, you can see this is sort of our evidence that they can be cooling. But the bottom line is that we're very uncertain on how much. So this is taken from the most recent IPCC report. It's sort of a summary of what we know. Anything that's red and going this way is warming. So that's where the greenhouse gases fall. Anything that's going this way and is blue is cooling. And then basically down here we have the sun. The take home from this slide is look at the size of, these are the uncertainties for greenhouse gases. Very small, and that's a lot of species. Whereas if you look at the uncertainties for the aerosols, it's very large. In fact, if you look at this uncertainty, it's basically the combination of these two is most of it. So this just shows how the impacts due to aerosols, we have a long ways to go. So basically, one of the things that's started to happen is with the climate getting warmer, we're starting to have other things not so good that are happening, one of which is wildfires. And this is a real concern in the western United States, as well as other regions of the world, as I'll mention in a minute. But basically, the wildfire frequency has increased by a factor of 4 now relative to the period between 1970 and 1986. The total area that was burned, and this is before the 2007 fires, is 6 times its previous level. So the number and frequency of fires are going up, the amount of area that's being burned is going up, and you can see basically the temperature is sort of tracking When it's warmer, we have more wildfires, more dry land. And this is taken from an article that was recently published in Science. But it's not just a United States problem. I can basically show you any continent in the United States. In particular, I thought you might be interested in this one. This is one period, one day. And each of these dots is a fire that's burning in South America. So, you know, it's a concern. I can show you something similar for the United States. You can go on onto, there's actual websites that you can go on and count hotspots or fires. And so this is one that I did for one day in South America in 2007. So this is the technique that Professor Thiemens mentioned we developed. It is a very unique instrument. It is the only instrument in the world that can tell you what's in the air that you're breathing right now. So it's an instantaneous snapshot. Normally, you use something like this, collect filters, take them back to the lab, and find out in a month or two what was in the air that you were breathing. Now you can actually turn this on and say, you know, should I be jogging today or not? Or why are all of these people going to the hospital right now? So this is a continuous instrument that gives you second-by-second information on what the particles are that are present in the air. It measures the fingerprint of every single particle. It can do 10 particles a second. So you get these fingerprints that you can link back to where those particles came from. So it's a very good way to understand the sources that are causing a lot of the problems. And we basically look at air in a lot of different locations. When we turn them on, they run continuously. And then we also collect samples still and then take those back and compare for health studies to try and understand the health impacts of these aerosols. And a study that we did with this instrumentation was in Mexico City, Milagro, in March of 2006. And one of the things we showed with our instrumentation that had not been shown before was the biomass burning. And this is both wildfires as well as clearing vegetation for agricultural purposes. So it's both. And basically we showed that it represented up to 80% of the aerosol in Mexico City. This is a picture taken from an airplane looking down. We were on the ground doing measurements. This shows the fraction of particles. This is data from our instrument. It's the only data slide that I'm going to show. It shows you the fraction of particles, so up to 100%, as a function of size. So right here is 0.1 microns. 2.5 microns, which is the standard we use for measuring pollution in the United States, is right about here. And what you see is a very strong size dependence of the pollution. And the concern is, as the particles get smaller, these are the particles that get transported more deeply into our bodies. So we actually want to understand how the chemistry of the particles varies as a function of size, because that is very important from a health and actually from a climate perspective. And what you see is that the biomass burning dominates across the range, but it becomes more prevalent at the smaller sizes. These particles are transported to every region of your body. The really tiny ones have been shown most recently to actually be transported up into your brain. So there's nowhere in the human body that these particles don't go. And they can transport, basically they're just very effective at transporting pollutants and toxins into our body. And once they go in, they stick and they don't come back out. Gases we can breathe in and we exhale back out, but these do not behave that way, unfortunately. So there's a convoluted problem where we've got the earth things getting warmer, we have more fires. As we have more fires, the thing we're finding is these fire particles have this other little effect. In addition to just absorbing light and leading to warming, they also affect cloud formation. So at the surface of every single particle, or every single cloud drop is a particle. You have to have that. And as you put more pollution up, you get more cloud drops, and you get longer-lived clouds. And so you start to affect local weather patterns. And these can actually lead to drought. They can lead to too much rain. It just depends on how much. And again, this is a really uncertain area. So how are we studying this? Well, we shrunk our instrument even further. This is the aircraft version. This is my student, Carrie Pratt, who did the shrinking and helped get it going. And this is the airplane that it flew on just recently in November of 2007. So what's the best way to figure out what the center of each cloud drop is? Fly through the clouds. So we did that. We went through the clouds and we pulled in particles that were above a certain size, and we looked at what is forming these clouds directly. And we learned an amazing amount in just a few flights. I mean, we found out things that we'd sort of been assuming were very wrong, and so we've been having to sort of rethink our vision of clouds at this point. But this just shows how if you have a particle, you can basically condense water on it, And then this is what a cloud drop looks like, and you can see particles in the center. And so they can form both water cloud drops or ice cloud drops. And again, the mechanisms to doing this and which particles are the very best at doing this is very, very poorly understood. And this is what we're trying to understand better. So in summary, we've developed a method where we can look at particles in real time. It's now being used by us and other researchers worldwide. It's the only instrument that currently can tell you what's in the air right now. As I mentioned, I think one of the take-homes from this is that aerosols can warm or cool. They're very complex. They really have large uncertainties. And one of the things that I like to point out is that they have much shorter lifetimes than CO2. And so CO2 and greenhouse gases we certainly have to consider. But the aerosols have timescales on the sort of the week timescale. So if we could figure out which ones are warming and which ones are cooling, they could potentially be a thing that we could ultimately use to help us. And so we really need to understand them better before we start setting policies. We have to have the good science in place quickly so that we can start making changes to make things better. So the last thing I'd like to finish with is just a little plug for the study that we plan on doing in 2010. We're doing it with a large German group and other people from around the world. These are some of the questions we'll be asking. We're trying to sort of understand the rainforest when it's still relatively pristine and see how these aerosols and pollution that's being transported into South America is affecting the rainforest. All right, so that's where I'm going to stop. Thank you.
I'd like to introduce our next speaker, who I suppose doesn't need to be introduced. In some ways, Mario Molina is a perfect speaker for this. He was trained in his bachelor's degree at the Universidad Nacional de Mexico, and he got his PhD in Berkeley, the University of California, Berkeley, and he did his postgraduate work with Sherry Rowland at the University of California, Riverside, and now he's with us at the University of California, San Diego. All of you know, I'm sure that the work he did in Irvine led to his Nobel Prize in Chemistry with Sherry Rowland and Paul Crutzen. His work since then, though, has been very impressive because there's three main interests here today and in general. One section of it that a lot of people work on is the measurement part. We love to measure things. We like understanding what's happening in the atmosphere. A second part is interpretation. When you make those measurements, you have to understand what does it mean. And that requires a certain amount of pure laboratory experiments to understand the very fundamental chemistry and physics. Third part is taking that and doing something that's important for society. Can you make policies? Can you make decisions for a country, for a megacity, for a small city based on the measurement? Mario does all three of these. He works in a laboratory understanding the pure physical chemistry of particles. He understands cities at a level of importance, and his work in Milagro, in case you don't know, that means miracle. No, I suspect you do. And also works with the Molina Institute, of course, in Mexico City, to try to make policies. And so you'll hear some parts of that in his talk. So thank you, Mario, for coming to speak with everyone.
Buenos días a todos. Me pidieron que
I was
hablara en
asked
español.
to speak in Spanish. Perfect. What I do have are my overheads in English, which I don't suppose poses a problem, but if there are any, ask a question. I was asked to speak briefly because the idea is rather to talk with you. What I would like to do is summarize, somewhat reinforce what you've already heard from our previous speakers. The idea is that I'd like to talk to you about what we are doing in terms of climate change, but also in the area of air quality and the combination thereof, the effects of one problem upon the other and vice versa. I'd like to just highlight again the issues of global warming, of which you have general information, no doubt, but just to recap from the scientific, international scientific community's point of view, the Intergovernmental Panel on Climate Change, made up of quite a few Latin Americans, 12 or 15 Mexicans, of which I am one. The important aspect of this group is that last year it published its fourth report. Every 5 years ago or so, it publishes a report which has a great deal of influence because it represents the consensus of the scientific community. So it assesses or the information and achieves global consensus. Thereby, it's important. Some brief findings as determined by this panel, which was recognized with the Nobel Prize along with Al Gore. But here we have a scale of 10,000 years, and the chemical composition of the atmosphere with certain gases, CO2 and methane. These are greenhouse effect gases because they affect the thermal balance of the planet. And what we see with this time scale is that with the Industrial Revolution, but really more so as of the second half of the last century, due to all of society's activities, all of a sudden its makeup has changed. In fact, if we were to see, just take a look and see how there's an explosion in terms of these various um, elements in the atmosphere. These two gases remain in our atmosphere quite a long time. CO2, 1 century, 10 years methane. Our planet works in such a way that within each hemisphere, because of the winds and such, it could be weeks or a month when the mix occurs between the two hemispheres. It's about a year and a half. So if we have gases that remain behind 10 years, it constitutes a global phenomena. We have fossil fuels, we have anaerobic fermentation, bacteria in the absence of oxygen, the digestive tract of livestock, or um, leaks and what have you. There are other gases, but these are the most important ones. Undoubtedly, this change, human in origin, is significant. Additionally, the temperature is changing. We don't know to what extent what the average planet surface temperature was millions of years ago because there were no thermometers, but we can detect through tree rings and corals and such. This can give us idea. We see that the average global temperature is rising. It would appear not to be a great amount, less than 1 degree Celsius, zero point 0.8, but this minimal change generates significant consequences. Why? Well, it's the mean. I can't really get into it too much, but we know, how when the average changes, they're interglacial, enormous changes, climate related, and that's only 4 or 5 degrees. So a minimal change can generate serious consequences ultimately. And what I wanted to sort of summarize in terms of this intergovernmental panel, one of the most important findings is that temperature is changing, its chemical makeup is changing, and these are linked. This is a consequence of the modification in its makeup and at the same time of human activities. We don't have the absolute certainty that this is the case, but the consensus after very detailed research is that the likelihood of this connection is being validated. That's over 90%, although we're not totally sure. We're not going to run the risk with that percentage of it's being natural, but we know, when there are glacial changes, certain consequences, the orbit of the Earth, and what have you. So within the scientific knowledge base, there is no reason to expect this kind of temperature change just because that's why it's linked to human activities. What are the consequences? A minimal change of temperature, and all the glaciers are melting. Well, maybe not all of them, but a few, two or three, maybe not, but over 100 are worldwide, and we see that up close. Also, the problem is that the glaciers, for example, in California or in China, are significant in terms of water storage for irrigation and agriculture. And in the Tibetan Plateau, the rivers which feed hundreds of thousands of people. So this could have significant effects from the perspective that it changes the way in which foodstuffs are raised. This is currently happening. It might be, though, that the issue of gravest concern that this small temperature change represents is the extremes. For example, we have more intense hurricanes ever more frequently, flooding. Clearly, in every continent, flooding has become more prevalent. So situations in Mexico, for example, Tabasco, here in the U.S., Hurricane Katrina, which impacted New Orleans, and other countries, we're not certain that a specific hurricane is the result of climate change, but with this kind of statistics, we know that the probability is going up. Sometimes in the past and previous century there were hurricanes, but not with the same intensity. Floods too, and also droughts. So the hydrological cycle is very susceptible to temperature changes. Here we see the amount of very arid land which has gone up in a 30-year period. So climate extremes, the temperature itself, there are more heat waves, but also in the winters have been colder because the average isn't changing that much. The heat of 2003, 30,000 deaths linked to that, vulnerable people in Europe. And this is an example of something which has occurred previously, but not at this rate. Climate change, of course, one could speak hours of it, but basically what we know of it today, particularly over these past several years with ever greater clarity, is that it is human in origin. And then the question is, what can we do with regard to that? It is, though, a reality. And here I'm going to repeat what one of our previous speakers said, and this is the link to air quality. This is a bus in Mexico City. It turns out that in the city there are other particles, dust or sawdust, is what most affects public health. What are the consequences of breathing in particulates? Because yes, the ozone, but really particulates are of greater importance. Today there are two examples. It might be that which most greatly concerns us is that it affects the health of children. The pulmonary or lung capacity of children clearly suffers. They're not able to reach their full potential when you compare cities that have poor air quality versus not. In LA, we did studies in Mexico City as well. Children aren't as healthy as they should be, and there are other issues. Asthmatics suffer even more as well. This is something which justifies significant steps being made to change this. And then people who are vulnerable, who already have weak cardiopulmonary systems, die much sooner, months or years, than they would had they otherwise not been breathing in particulates. These are some of the most important public health effects. Well, as one of our speakers mentioned, this is no longer limited to a city, but this is a clear public health issue, and we see it's global too. Here we see this brown cloud from Asia. Our colleague Ramanata from the Scripps Institute of Oceanography has studied it in great detail, and we see that this kind of pollution is able to move from one continent to another, in this case, the US. So the particulates, as compared to CO2, do not remain in the atmosphere except for a matter of weeks, maybe a few short months, because rains do away with them, but the greenhouse gases do not. So with the gases, the problem that exists is that we're seeing the accumulation of many decades. Particulates, fortunately, are eliminated, but on the other hand, the sources of particulates are so significantly important because of their scope that they represent a global issue. Here, what I'm showing you is something similar to what we saw previously, but with a small difference. This, which we call, it's a way of comparing the effects in climate of the various component. What happens is that this intergovernmental panel is quite conservative. So the 2007 report only took into consideration clearly established results through 2006, basically. But it turns out that over these past several years, it's seen that black particles greatly contribute, or darker particles, to climate change. This is not yet included within this report, but we do know it to be the case. So this is black carbon. Recent studies clearly indicate that it had not been appropriately estimated in these studies. All of this science is relatively new. So it turns out that forest fires, biomass burning, industrial production in cities, and so forth, it's not only an issue of air quality, but also an issue which affects the climate. And that is why it is important to go after both issues together. It turns out that many measures which we could take with regard to air quality, which benefit climate change and vice versa, the only thing that we have to take note of is that certain kinds of particulates come from CO2 burning, especially in the US and in China, because of the fact that a great deal of electricity is generated not with oil products, but with carbon. For example, in Mexico, we have very little of that, most of it from oil or petroleum. But if it's not very clean, it has sulfur, and sulfur is what leads to this sort of foggy white layer. But the justification cannot be to contaminate or pollute to counter climate change. We have to really resolve all of these issues independently. So one of the concerns is that we need to rid the atmosphere of these sulfur particulates, and this will affect climate change even more. There is no doubt, though, that these carbon-based facilities are some of the worst in terms of CO2, so there's a great sense of urgency that there be an agreement so that the carbon generated electricity is no longer an option. But how can we resolve this? The issue of global pollution, or maybe the most important part, as I said, was CO2, although there are other gases. Here we see emissions based on time breakdown. Red represents what will occur if we don't do anything. This pursuant to the intergovernmental panel. So we need to bring down these emissions. We cannot continue working with the electricity, the development model, and what have you in various countries. We must bring this down significantly, and the consensus is that we should not let the temperature go up by more than 2 degrees. It's very dangerous. It could change such that it could drastically impact several communities. So, more than 3 degrees would be extremely worrisome. Hopefully, not more than 2.5 degrees. But this requires uh, emissions reductions. That's why, for example, today G8 and these various industrialized countries committed to reducing them by half in 2050, so that we stop at the green line, if not the yellow, leaving aside the red. It's an enormous challenge, particularly in terms of energy use. And so what can we do? These are the same emissions lines, business as usual, above the green, and we want to come down into the blue region, but there is no magical solution. A great many measures need to be taken at the same time. First, we need to be much more efficient. We just, for example, in terms of transportation, technologies exist, cars, buses, etc., that require a great deal less fuel, and so these are being launched, especially in industrialized countries. But for this to happen in Mexico, but not only transportation, housing, better isolation, and I'm not going to be able to talk about this in great detail, but we need alternative energies. Solar energy is more frequently used in Germany than in Mexico City, and there they have a great deal of clouds and poor climate. There's no excuse. The technology exists. It's still expensive to generate electricity with photovoltaic cells, but the idea is that it goes down. Even nuclear energy, provided it's done cautiously, and that's another subject which we could discuss. Biofuels, again, are a solution, but require a great deal of care. Many recent results show us that the way it's happened doesn't always work. For example, in the U.S., to extract fuel from corn isn't positive for air quality or any other reason. But it's also strategy not to be so dependent upon the Middle East. That's not exactly how we should proceed. There are other areas, maybe cane alcohol, provided it doesn't affect food stuff. There are issues, but it could be part of the solution of obviously forest management. The atmosphere regenerates oxygen based or with CO2 based on photosynthesis. Part of the problem is emissions based, and the other part is that we have deforestation. There are less green plants which balance or restore atmospheric balance. There needs to be an international agreement. Hopefully, we could begin to see this in 2010 in Copenhagen. There are many expectations. Mexico is working as a leader in industrialized countries, China and India. The idea is that they take part as well. Everyone must participate. It's not only the wealthy countries which need to work on this, but there has to be a cost in terms of emissions, such that that cost motivates the use of alternative energy or energy savings, and this is already somewhat occurring because of high gas prices, but it's not happening with carbon. Carbon hasn't gone up in terms of price, so we have to make sure that carbon consumption doesn't go up, because that's really awful. But anyways, this is another interesting subject. But in terms of pollution, and by way of conclusion, it turns out that beyond having more efficient vehicles, there are all these new technologies, catalytic converters, volatile organic compounds, nitrogen oxides with no catalytic converter, and how technology goes up. And then the red indicates that this technology does exist. In Mexico, as an example, is working with the we're working with the government so that the new vehicles, whether they be diesel or gas, are low pollutants. For this, fuel with very low levels of sulfur is required. We're going to produce it in Mexico, but also in other parts in Latin America. is lagging behind a little bit. So there are technologies. There is no excuse not to have clean air, but it is an enormous challenge. And there are challenges with the transportation system. Mexico City maybe is an extreme example of traffic issues who require efficient transportation and restriction in terms of vehicle use. This is how we'd like to bring down sulfur content in gasoline, diesel, or otherwise these are the projections in Mexico at Petróleos Mexicanos that they're lagging a little bit behind, but we can see how they've done it in Japan and Europe and the like. All right then, I have a couple more slides, but I'm going to stop here and simply would like to summarize with the following idea. We have enormous problem on the planet. It cannot be solved by a single country, Peru, Argentina, Chile, or what have you. Even if one were to bring down the greenhouse gases, the remaining countries continue at their levels. So that's why we all need to work on this with an international agreement. However, atmospheric pollution is more localized. It's something that can be dealt with locally. However, it turns out that part of this pollution, which comes from the cities, well, I didn't really talk to you about the Milagros program, but the idea was to see how in Mexico City, or rather what happened with emissions once they left the city, how they affect the surrounding areas and so forth. So not all of the results have been fully analyzed yet. It just goes back to some of the concerns which were raised. The fact is that also is that this situation where we have a contaminating we have contaminants in cities and not this. There's a more recent phenomena in terms of science. There's a great deal of uncertainty, and here San Diego, the group in San Diego is renowned as experts in this field, and we hope to continue to contribute to resolving these issues through research on the one hand, but also working with the various governments at a local level, at a global level, in order to incentivize them to deal with these issues. I think I'm going to stop here so that we have enough time for questions and answers.
I guess this is a perfect opportunity to, I'll avoid introducing myself and saying the sort of things you'd like to say about yourself. But so anyway, I'm Mark Thiemens, and again, thank you for coming here. And I'm going to follow up a little bit on what you've heard and talk just from pictures on things that we do and why it might be interesting for you. The point I want to make, you often hear in political circles that it's impossible to change the environment because the Earth is so big, there's nothing we can do to change it. And this is just a picture from space. And here's the entire atmosphere of the Earth. And then the Earth, of course, goes way down through the floor. So the point is that this little tiny layer here is actually quite small, and our ability to change this is real. There's not much there, and we can definitely change it. Now, one of the issues that we're interested in that can change things is the issue of ships. This is one of the largest unregulated sources of pollution in the world, and they emit the particles into the atmosphere that you heard from both Professors Prather and Molina that are important. And it's unregulated. How much is it? What does it do? And where does it go? We don't know well. This is a model by Paul Crutzen, who shared the Nobel Prize with Professor Molina. And this shows where the ships are in the world. And this is to make the point that it's important for everyone in this audience, because you can see that the ships coming from this part of the world go along the coast, and a lot of them end up going through the Panama Canal. So everyone in this region can be influenced. And as you heard from Professor Prather, these are the particles that are important for not only climate, but health. You breathe them because they're small, and they get in your lungs and your body, and if they're really small, they get in your brain. So that's a big issue. Then of course you can see this part of South America and down through here is very heavily influenced. But again, this is a computer representation. These are the guys that caused the big problem. You can see as much as 250,000 tons of oil getting burned by these. And these are the ones that are going down your coastlines. And some of them are the big container ships, and these guys are dirty. These ones that bring the big ships in and out, there was an article this week in the New York Times on the front page that showed that these ones here are a source of carbon in many of the ports of the world. What they put out, besides being particles, is just simply from the particle standpoint are bad for you. Compositionally, they're acids. So they're bad for you and they're bad for the environment. So again, here's a picture showing you where it's a big issue. How much is it? How is it affecting the local regions? We don't know. And for that reason, the three of us and our colleagues on campus and at Scripps Institution of Oceanography are using this spot here as an observatory. You can't measure the whole world. The three of us would love to have the resource funds to do it, and we would make a very good attempt at it, but you can't do it. So you have to choose places that work. And for two reasons, this spot works good. First of all, in terms of what's coming in from the ocean from ships and the long-range problem that you heard about, this is a good spot. Secondly, it's close to us. We can walk out here and do it. And the instruments that all of us use, especially Professor Prather, are really complicated. And even though you can put them in an airplane, they still need somebody to babysit it. And it's just because they're really complicated instruments. There are multiple lasers, there's a lot of voltages floating around, and an extraordinary amount of information. So being able to use them where you can get to them easily is a big advantage. So for that reason, we're making this as an observation place, but we want to understand because of what's going on here, because we live here and there's sandpipers and surfers too, but also because it can be used as a model for the planet. And so the ship one is one of the questions that will come out of this, we hope, and try to make some sense of what does it mean for the rest of the world. And you can see the rest of the world is especially influenced as Latin and South America. Here's the second issue. Now I'm going to show the long-range transport from Asia, but everyone is affected by everyone. And this is a satellite picture of what happened in May 3rd, and we've been measuring at this spot on the observatory for more than 3 years. And we were measuring at this time here, and around May 7th or 8th, we thought, we see China. And so here's May 3rd, here's a bubble of ozone pollution coming across the Pacific Ocean, and here we are. May 4th, here it is, spread out, hasn't reached the United States, and boom, here it is. Exactly the time when the measurements, and I won't tell you what the chemical measurements are because you'll need coffee and you don't want to hear a chemistry lecture and you'll fall asleep. But because of the magic of chemistry and whatnot, we could see that it hits here. But notice what happens in these. This is why long-range transport is important. It's local, but it's global. So notice this hits here. And when I tell my friends on the East Coast, look, if I tell these people here, they say, well, so what? It's California. What do we care here? It's California. You guys deserve it. But you can see another day, and now here it is in Arizona. And then they still say, well, it doesn't matter because people go to Arizona to retire, and so it's not a big deal. But you can see that, look, now it's spreading across the rest of the central part of western United States, and then you follow it another day, and here's the next one, and here's the next one lined up behind it. So it's global. At the same time, I did it because we're studying here, so I'm prejudiced, but I could have easily given a same talk and showed that the stuff coming out of here from these people living here in the western United States in the same period of time ends up here. And at the same time, there's things coming across the pole. And so the world is connected to everyone, and no one is innocent. That's the point to be made, is that you can't say, oh, it's a US problem, or it's these people over here doing this to us. No one's innocent and everyone's guilty. Now, one of the issues that we're interested in besides this is directly important. 4 years ago, we set up in a station down here outside of Loja in the higher altitude rainforest. It's only about 3,000 meters, but it's reasonably high because number one, it's remote. Number two, my biological friends told us that in this area of the rainforest, there's major extinctions. Species of plants called epiphytes that make their living from only air. They don't have roots. So they were disappearing by the thousands. But nothing had changed in this area. And then we've gone down into Peru, and then we want to go up into this area in January and try to understand why. What's happening? So in the beginning, we thought probably things are going on in this region, perhaps biomass burning, that affects it here. And so we've spent 3 years measuring air, water, aerosols, streams, and fog. And one of the things we find that's very interesting is the following. It's been known since Charles Darwin. By the way, Charles Darwin has his 200th birthday in a year, so you still have a year to shop. Abraham Lincoln does also, so you can do two of them at the same time, and if you're worried, now's the time to do it. That has nothing to do with the talk. So the Sahara Desert emits dust that crosses the Atlantic and goes into this part of the world, mostly in the summer. And it was Darwin who discovered this. If you read it, and I advise it, it's a very interesting book, The Voyages of the HMS Beagle, he talks about the dust that's here could only come from the Sahara Desert. And he was right. And a gentleman named Joe Prospero at the University of Miami has been measuring that dust since the 1960s. When I was a student at the University of Miami in the 1960s, he was just starting that, and I remember him talking about it. And if you're doing the mathematics in the 1960s at the University of Miami, I was 4 years old. And so he's been studying it since the 1960s. But what's interesting is the following, that's probably even more important, is in the winter, the dust storms moved to the South Sahara in Chad. And the winds in the winter come out and cross, but they go straight into the mouth of the Amazon River. Now this has always happened. 30% to 40% of what makes the Amazon grow and is rich comes from here. It needs this dust. But now what's happening that's different is that when this dust is coming, it's exactly when all the biomass burning is going on. And there's a buildup in oil refineries in Western Africa. So instead of being clean dust, Charles Darwin sort of particles, they're now getting coatings of chemicals crossing through here. And you heard Professor Prather talking about this with the measurements she's made and why her aircraft measurements are so important, is what happens to them in this process is really important. And her measurements are really the way to understand this properly in what's going across here. But what happens when it comes into here, and if you follow the air masses, which we've done, they cross, and you can see this dust all the way into Ecuador. How much is it? What is it? We don't know. We only know that we can see it. So that's why for scientists it's an interesting question, but these are issues that are important for society, and we have to understand this, and that's part of what's being done. And that's why it takes, as you heard Professor Prather say, for example, in her 2010 effort, these large programs like Milagro is to understand these issues in a large way. Because if you want to make a decision how to protect areas, sometimes you have to include the whole world, and sometimes you have to include small regions. Most of the time, it's both. So being able to put the science and decision making together is also important. And of course, here's the last thing I'll show you, is that here's that region, and the bad news is that with the temperature getting warmer, and you saw Professor Molina's slide, as it gets warmer, you make more dust. And Professor Prather said it also, is that you make more dust, and so this problem gets worse with time. And so we need to be able to predict what's going to happen. And this is just a picture to show you. Here's Western Africa. You can see the size, and here's the Straits of Gibraltar. You can see the size of these dust storms, and actually the better picture was Professor Prather's. So bottom line, it's one planet. You can study one region here, here, and here, but if you really want to do something right, you have to understand the whole system. So I'm going to stop, so thank you for coming.